Hello everyone, I hope you are doing well. So in this video, we are going to discuss Geeks for Geeks problem of the day, and today's problem is transform to prime, and it is a medium level problem. So the problem statement says that we have been given an array of n integers, and our task is to find the minimum positive number to be inserted in the array so that the sum of all the elements in the array becomes prime, right? Now again they have said minimum positive number, but as you can see 0 is allowed here because 0 is the output here. Whenever we talk about 0, we say that it is neither a positive nor a negative number. So this statement like itself contradicts itself. This is the first thing that I wanted to point out. Whenever we talk about all the positive numbers and 0 as well, we generally use the term non-negative number, right? So it is like this here only, but whenever you see the term positive number, we are generally considering numbers starting from 1, right? 0 is never included, but here you will have to take 0 as well. So anyways, the problem is very simple, simple in the sense like the idea is simple. So let's say you have these array elements, right? So 2, 4, 6 and 8 and 12, right? So they have themselves written that the sum of the array elements is 32, right? Now once you have the sum 32, that means whenever you add a new value greater than or equal to 0, your sum is only going to increase. So now the question becomes, how can you increase this sum value so that it becomes a prime number? Now you want this increase to be minimum as well. So you would definitely take the closest prime number after 32 that occurs in the primes list, right? So the closest prime number in this case will be 37, which is the prime number after 32. If let's say the sum was 37 itself, then you will add 0 because it is already a prime number. But let's say we are currently at 32 and we want 37, so the difference is going to be 5, right? So this is the value that we want to add. So basically the question has reduced to the next smallest prime, right? And if the current number is prime itself, then it is not a problem as well. So this problem, next smallest prime, can easily be solved with binary search if we already have a list of prime numbers. So let's say I have this list of prime numbers 2, 3, 5, 7, then 11, then 13, then I believe 17, then 19, right? So let's say I have a list of these prime numbers. Now I want to find out what is the number after 8. So I can easily perform a binary search here, and this is going to be this one. So whenever I use a lower bound function, let's say if I use a lower bound function, inbuilt C++ STL function, this is going to give me the element greater than or equals to my search key, right? For example, if I search for 8, I'm going to get 11. If I search for 13, I'm going to get 13. But if I search for 14, I'm going to get 17, right? So this is how you can easily perform a lower bound function on the primes list or the array consisting of all the primes. But the task now is to find this primes list, right? So that is our main task now. So now if we have a look at the constraints, the sum of all the elements is only up to 10 raised to the power 6. If the sum of all the elements is up to 10 to the power 6, then the maximum answer in any case, or the maximum prime number in any case, will be 10 to the power 6 plus 3, right? Because this is one of the prime numbers. This is one of the prime numbers, and if the sum of elements is itself 10 to the power 6, then the next prime number will be 10 to the power 6 plus 3, right? So this is the maximum possible prime number that we have to take. Now that means we will have to compute all the prime numbers up to this particular range, 10 to the power 6 plus 3. So how do we compute it? If you have a look at the time complexity, it is n log n. So if you are already familiar with this particular concept of Sieve of Eratosthenes, then you must be able to understand what they are trying to say. So there is a very popular method of finding prime numbers that is called Sieve of Eratosthenes, and it works in O of n log n. We will not dive into the mathematical proof why it is n log n, but I will give you a slight idea of what sieve is, and you can always find like a lot of YouTube solutions or YouTube videos on Sieve of Eratosthenes that have explained the topic in depth. Here I am just going to discuss a very brief idea of sieve. I am not going to explain the whole thing in very detailed manner. So in case you do not understand here and you want to explore it further, you can definitely check out some other channel on YouTube where they have explained it properly, because there are a lot of videos already. That is why I want to reuse them and not waste any time here, right? So let's say this is my array, and let's say these indexes are, let's say 1 2 3 4 5 6 7 8 9 and 10. Now each of these indexes is going to store whether the current element is prime or not. So if I'm at index 4, it is going to tell me whether 4 is prime or not, right? Now let's say initially I say every number is prime, so I'm marking 1 or true, whatever you can say. Now I'm going to remove the one from 1 first of all, right? Because I know that 1 is like neither prime neither composite. So now I start from 2, right? I know it is a prime number, but if a number is a prime number, then it is going to have multiples of itself, and those multiples are not going to be prime, right? Let's say I'm talking about 6. So 6 has a divisor 2, right? Or 6 is a multiple of 2. You can say it in whatever way you want. So what is the definition of a prime number? A prime number is a number which is only divisible by 1 and the number itself, n. But if I see 6 is divisible by 2 as well. It is also divisible by 3, right? So that means it is not a prime number. So I have just twisted the statement in a way. Let's say I am standing at 2. I am saying that all multiples of 2 are composite. Why? Because those numbers are going to have a divisor called 2, right? So this is my idea. Now what I am going to do is I am going to mark all multiples of 2 as false. So this is false, this is false, and this is false, and this is false, right? Now I come to the next number. I see that this number is prime, but if this number is prime, all its multiples are going to be composite or non-prime numbers. So I go to all of its multiples, that is 6 and 9. 6 is already marked as false, so I mark 9 as false as well, right? Now I come to 4. It is already a composite number, right? And all the multiples that are all the numbers that are multiple of 4 were also multiples of 2. That means, let me say it once again. I am saying that all the multiples of the number 4 were also the multiples of 2. That means all the multiples of 4 would have already been marked as false. So I do not need to mark all the multiples of 4 again, right? So I just skip this particular composite number and come to the next prime number. So what we generally do in Sieve is we skip all the composite numbers and do not mark its multiples, and I was just trying to explain you why we actually do so, right? Now I am at the next prime number, that is 5. Now I have to mark all of its multiples as false. So 10 is already marked false. The next multiple would have been 15. I would have also marked that, but again 15 would have been marked by 3. Then I would have find some multiple like 25 which was not marked by any other number and then mark it false, right? So basically this is the whole process. You start from the left. As soon as you encounter a prime number, you mark all of its multiples as false and then continue the process till the size of the array. So the total complexity is n log n of this method, and n is the size of the whole array or the maximum number that you have. So once you have all of the prime numbers, the prime numbers will be marked as 2, such as 2, 3, 5 and 7 after the whole process. So you can just push back all of these numbers into a separate vector, and then you will have the primes list which you can now use here, right? The previous method that we were discussing. So this whole process will take you n log n time for computing the prime numbers. Now you can obviously watch some other videos on YouTube to know more about it in detail, but this was the whole idea that we do. Now what I have done is, actually I was getting TLE on this particular problem, so I had to use a little trick here. The thing is, they have multiple test cases, right? So they have multiple test cases in the same problem. Now my value of n in this particular case is 10 to the power 6 plus 10, right? So this is the upper bound that I have taken. If I run this particular for loop, like the n log n part, for multiple test cases, then it is going to give me TLE, right? So what I have instead done is, I have initialized a computed variable with 0 and my prime vector in the global state, right? So now if my primes are not computed, only then I am going to execute this part and mark my computed as 1. Right. So when the same function gets called for the next test case, this computed will be true. That means I have already computed the primes and hence this part will not be executed. Right. So normally the way you do in this kind of things is that you define all of this in the main function here. Right. Here somewhere here. Right. Before even calling the test cases. But here we did not have that option because we cannot change this part, right? So what I instead did was I used a global compute variable to store whether I have calculated the primes or not, right? So you see I have initialized an is prime vector which is going to tell me whether the ith index is prime or not. So I mark 0 as 1 as non-prime and I am starting a loop from 0 and going till square root of 10 to the power 6 plus 1. So like why only square root? So actually I have written it as I into I is less than 10 to the power, let's say 1e6 plus 10, right? So I have written it like this, but if you perform square root of both sides, so it will be equals to I is less than equals to 1e6 plus 10, right? So this is equivalent to this one. Why I have done it this way? The reason being simply, if I have to calculate the square root, it will be like calculations in double and it might also have some precision errors. Moreover, it takes more time, right? But here I into I will be in integers only, so it is always better to use such method. Now what I have done is I am going only till square root of I. This is something you must already be familiar with. That means if I have any number n, then at least one of its prime divisors will exist till root n. So if I want to know whether the numbers till 10 to the power 6 plus 10 are prime or not, then for each of those numbers till 10 to the power 6, I will have at least one prime divisor till square root of this particular value. So as you see in this particular case, only one divisor was necessary to tell whether this number 10 was composite or not, right? Because 2 will also mark it, 5 will also mark it, but we don't need 5 if 2 has already marked it as non-prime, right? So we need only that one divisor. That is why we are going to root the maximum value. Now if the current number is prime, I am going to start my loop from I plus I, that is the second multiple of I, right? And I am going till the last value and I am incrementing j by I each time and setting s prime as 0. Now I am going through all the numbers. If the current number is prime, I am just pushing back into the prime vector. So this was very simple, and now we have like this particular part where I calculate the sum of the whole array and I use the lower bound function to get to the position which is greater than or equals to my sum element. So I have got a pointer to that particular position, that is why I can dereference it and minus sum from it, and that will be my final solution. So I am just submitting it to show you that this particular code works and the solution is absolutely correct and in the expected time complexity, right? So you see it passes all the test cases, and the space complexity is something different. We can never solve Sieve of Eratosthenes or similar time complexity with over fun space. You will have to maintain this S prime vector, right? So that is something we need to take care of. So that was it for this particular video. I hope that you guys were able to understand the solution. If you guys did, then consider dropping a like on this video and don't forget to share thoughts in the comments, because your engagement with this video really helps the YouTube algorithm to understand that this video is actually helpful for you and it will be able to reach much more people like you who want to keep solving new problems. So that is it for today. Till the next video drops, keep coding, stay safe, bye bye.